Good morning, everyone, and welcome to Grade 11 Functions. Today, we are learning the answer to this question. What is a function? And why the heck is Mr. Jennings so excited about functions? Like, why does he like this course so much? Well, the answer to this and many more questions are coming your way now. So you all have your handout. It's here, and so that's great. And we'll be filling that in together as we go, so follow along with your handout. So the first thing, relations and functions. Okay, so we've been looking at a series of relations and various relations in other math classes. Relations are patterns that exist between two variables. We can represent relations as ordered pairs, tables of values, graphs, or equations. Okay, so if you think of a circle is a classic example of a relation. A circle might be modeling the orbit of a satellite around the Earth, and we can predict the location of that satellite with the equation of a circle using time and various different trigonometric functions, right? But the shape of the orbit would be a circle, right? That would be an example of a relation. Functions are special types of relations. Every value of the independent variable corresponds to one and only one value in the dependent variable. Okay, so that means every function is a relation, but not every relation is a function. Okay, so let's do a little bit of a thought experiment. I'm just going to pause the video and we're going to generate some values up on the board. Okay, very cool. So we have over here marks from 0% to 100%. We call this the dependent variable. It depends on something else. And you've identified amount of homework you do is going to determine, to some degree, the marks you'll get. All right? So now let's create a scatter plot of some students, and how are we going to measure how much homework they do along this axis? How will we be measuring that? Hours is good. Hours per day? Hours per week? Let's do per week. Hours per week of homework. Hours per week. Now don't get confused by this per. We're not going to have a rate of change here. We're just going to be doing it over 1 week, okay? So it's not like, miles per hour or something that would create a line. All right, so hours per week, and what's a good upper limit? 14 hours, 2 hours a day? Is that a good upper limit? Okay, we'll say 14 here, 14 hours per week. We have 7 hours per week here. That would give us something like, 5. Oh, this is an ugly scale. So let's change our scale a little bit. We're just going to go to 20, just to make this a little cleaner. All right, and you can sketch a graph if you want. 10. Some students might be doing about 3 hours of homework a week. That'll be 21. So here we'll have 20. So 3 hours a day, 20 hours a week. Maybe 10 hours a week is maybe is that average? I don't know, an average amount of homework to be doing a week? 10?
I'd say like 7.
7 is a good average? Okay. All right. And maybe some students are just doing stuff in class, right? So now let's take some ordered pairs and we'll plot them. Let's say we have 3 students who all do an average of 10 hours of homework a week, all of them. What does the first one get as a mark? 10 hours of homework a week. What's he going to get, Damon?
75.
Sorry, what did you say?
85.
You said 85. Okay, so we have one person getting an 85. This is the point 10, 85. Great. The second one who does 10 hours of homework a week, what mark does he get? Sander? 75. Okay. So this is the point 10, 75. All right, and then there's one more student who does 10 hours of homework. Riley, what's his mark? 50. Yeah. Okay, so he gets a 50, which is over there. It's 1050. All right, cool. Now, there are some students that only do 2 hours of homework a week. Are they going to generally have higher marks or lower marks than this group?
Lower.
Likely lower, probably. Okay, so 2 hours of homework. And what mark do they get? First one? 60, 65. Cool. So this is 2, 65. All right. And then there's one more that does 2 hours of homework. What mark do they get? 55. Cool. 255.
You did 2 hours.
Yeah, it's a tough world. Yeah, okay. Who knows? There may be some other factors involved in that 50. Maybe that's just 1 week, and then the next week they bounce back to a 90 or something. They change their study habits, start using this time more effectively. And now there are a few students that do 20 hours of homework a week. But we'll say there's 2 students that do that. What's the first mark? 97. Okay, so we're almost at the top of the scale there. 20, 97. And there's one more student that's way up there. 67. Okay. So there's one student that's getting a 67. All right. So that's about there. Okay. 20, 67. Okay. So now we have 7 data points. What we have here is something that shows the relationship between hours studied per week and the marks that people receive. If we had more data, Brody.
That makes sense because if you're doing 20 hours a week, you're probably going to get tired. So
tired, yeah. It might not be a line where you keep on doing better the more you study.
It might be a parabola.
It could be. There could be an optimum value somewhere in there. Kaboom! Yeah, and so you want to find that optimum value for you. And Brody, maybe your optimum value is different than Sanders' optimum value is different than Sarah's optimum value. Because that's about knowing yourself and your own study habits. But anyway, what we have here is a relationship between hours studied per week and marks received. Okay? The two things are not exactly the same, but this one, the independent variable. Generally, we think of independent variables as the ones you get to pick or choose, okay? Like, they're the thing that determines the other thing. We would say number of hours of homework done per week determines to some extent your mark. We don't think of it the other way. Your mark determines how much homework you do. It's not like your teacher gives you a 93 and you say, oh, well, I better do 17 hours of homework a week. No, it's like, because you did 17 hours of homework, you're going to get that mark. So that's the relationship between independent variables, which we usually graph along the x-axis, and dependent variables that are determined by that. Now, this is a relation. It is not a function. Why is this not a function? According to this definition that we have on the PowerPoint.
There's 2 variables?
Well, there are 2 variables here, but we can have functions with 2 variables.
I don't know.
But there are some problems with the way our variables and our data points specifically are organized. Ryan?
Because there's like more than how many answers.
Yes. We have x values of 2, 10, and 20. The students that we polled either study 2 hours a week, 10 hours a week, or 20 hours a week. From our data points, we notice that this x value of 20 produced 2 different y values. That's fine for relations, but it's not fine for functions. This value, x equals 10, produced 3 different data points. That's fine for relations, but that means it's not a function. Okay? But now, what we have there is a scatter plot of our data. And if I were to say, well, you tell me how many hours of homework you did, and I'll try and use this data to predict your mark. I'll try and predict the future with this. What I then need to do, this is going back to review some grade 10 content, is to create a line of best fit. All right, so I'm going to now create a line of best fit. And I'm not going to create a parabola of best fit, okay? I'm not going to create a curve of best fit, but maybe that would be even more accurate, given that you might have diminishing returns going that way. So I want some of my data points above and some of my data points below the line, and I want them close. In Desmos, you can get a perfect line of best fit. Here, we're just going to be close. So see, I'm between those 2 data points. I'm going through the middle of this cloud, and I'm going through the middle of that cloud. So this will be a line. I could use this line to predict if you were to study 0 hours, you would be likely to get, that looks like about a 55 or a 50, okay? Based on this point, there's 55, and it looks like I'm coming down to it. I could use that line to predict, what if you wanted to, quote unquote, guarantee yourself 100, how many hours would you need to study? Well, I would look for the intercept of the line y equals 100 here. and it looks like it would end up being, maybe 30 or so, 30 hours a week, if you don't imagine diminishing returns. Now this is a line. I can use that line to predict. You tell me, I do 15 hours of homework a week. I would say, well, you probably are going to get like an 85, probably based on my data here. Like if you do 15 hours of studying a week. Actually, some people are shaking their heads. Maybe they're like, no, I want more than an 85, man, if I'm going to study 15 hours.
Yeah.
Okay, this line, is it a function or a relation?
Line is a relation.
A line is a relation, but is it a function?
Yes.
Yes. Yes. Yes. Why? Why is this a function and not simply just any old relation? Do you want to answer or do you want Riley to answer? Go ahead, Riley.
I'm totally guessing here, but it's because it only has like one set value all the way through.
That's right. Any one value of x
You are right.
will only produce one y value. That means if you tell me the x, I can tell you one and only one y. Okay? So compare that to a picture of a circle, and I'm just going to put this in the middle here. This is a circle. I could find the equation for it. A circle like that would mean nothing in the context of marks versus time. But just bear with me for a second. That circle, one value of x will often have two values of y. It's actually only two values of x where there's a single value of y. This one and this one. All those other points of x have two values of y that they can output. And the reason is that y squared that's in there. The y squared plus x squared equals r squared. Now because of the squared, we get a plus minus, we get two values of y. A relation, not a function. A line is a function. Yeah, because there's only one value of y that corresponds to each value of x. A parabola. Is a parabola a function or just a relation? It is a relation, but is a parabola a function?
It only returns one value.
Yeah. Parabolas only return one y value for any given x value. So they are also functions. They can a single y value could be associated with two x values, but that doesn't exclude it from being a function. And we'll get to some more examples of that in a second. So by the end of this lesson, you want to be able to do these things. Here's our learning goal. You want to be able to identify functions represented by tables of values in ordered pairs. So up here, I can recognize these this table of values or these series of ordered pairs that we drew up there does not return a function. It returns a relation. If I take an average of that, then that's a function. That I can use to predict one average mark that you'll have based on numbers of hours studied. Mapping diagrams are something we'll take a look at as well, but we're mostly interested in this course in equations, graphs, and tables of values. And these are the three main ways that we look at relations and functions in mathematics and how we're going to understand functions throughout the course. So here are some examples of functions that you're going to see in the world that might relate to some of your career goals. For example, in medicine, when you administer a drug to a patient, that patient will take the drug and the drug is absorbed, and you'll see here is the onset time of the drug. We would determine that when the concentration in the blood or in the tissue that you're treating reaches the therapeutic range, reaches this range where the drug will have an effect. That's the onset time. That's going to be the drug dissolving in the stomach, the drug entering the bloodstream, and the drug beginning to take effect through here. The maximum concentration is reached, and that's when the liver is already starting to kick in and metabolize that drug and reduce the concentration of the drug over time. And eventually the liver and other metabolic systems in the body are going to metabolize that drug until it drops out of the therapeutic range and down into basically you have no more drugs in your body range. Okay? Now these curves, we can create mathematical equations to study them. We can create tables of values to look at them, and we can look at graphs like this as well. This is a function. Any particular time will have the predicted concentration of drug in the body, and it will only have one value when we look at a certain time versus that concentration of drug. Another example of a function is money. And that gets us to our challenge problem for today. This is an example of you have some money that you invest, and that's the blue, okay? That's your initial value of money. At 0 years, you invest that much money. Oh, here it's 1,000. That's pretty cool, okay? If you're getting interest with no compounding, and this is the same percentage of interest. In our example problem, it's 100 times different, okay? But this is with the same amount of interest. In the beginning, there's no difference between simple interest and compound interest. But did anyone notice while you were considering this situation, you have $1,000 to invest, and every year they'll add $1,000? Did anyone realize that that creates a line?
Oh, yeah.
Yeah. We would have our M is 1,000. Every year it grows by 1,000. So when X increases by 1, the line would increase by 1,000. And our initial value, our B, would be 1,000. Okay? And that would give us some amazing growth over 1,000 years, sure. But compound interest, you'll see, is a curve. There, the rate of growth is changing. So even with a small percentage of money, everyone cares about money, right? So we can take a little bit more time and look at this example. Let's go ahead and graph it. So to graph this, we talked about y equals 1,000x plus 1,000, okay? That is the situation where we invest $1,000 and every year they add 1,000 to it. Except I should say this is x minus 1, right? Why do I have x minus 1 in there? Well, at year 0, I should have only $1,000 in there. So actually, no, I don't need x minus 1. It's fine. That was crazy. Yeah. Sorry about that. Anyway, thinking out loud. So here we go. I can't see enough of this. So let's take a look at changing our scale so that we can get more useful information. X, I want to see how many years? I want to see 1,000 years. Okay. I want to be able to see 1,000 years of growth. Y, I want to see a lot of money here. Let's say, I don't know, what, like $1 million? 1, 2, 3, 4, 5, 6. Okay, there we go. Now I can see it. And there, it crosses $1 million way up there. Maybe I will show us $2 million just to be sure. Okay, there's 2 million. Okay, now let's click away. Here is your money growing with simple interest over 1,000 years. After 1,000 years, it just passes the $1 million mark. Okay, so in 3021, when you're woken up from freezing, you're going to have $1 million, which will probably be enough to buy a milkshake. Okay, now it's just a little inflation joke for you. Okay, next, we want to look at compound interest. Later on in this course, when we look at exponential functions, we're going to discover that things like corona or money all grow exponentially. And the way we'd set that up is we'd say, well, y is going to equal, y, remember, is our total money that we have, and our independent variable there is time. So one function that we could have is, well, we're going to invest $1,000. We're going to invest it at 1% interest. So you'll notice here, this is 101%. All right? Yes, by all means, Ryan. This is 101%, and I want that amount of interest every year. So if I use x as the exponent, this will show me the value of my investment as it grows by 1% per year. Why is that happening? Well, every time I increase x, I'm multiplying my money by another percent. So if I have x is 2, so after 2 years, my money's grown twice, so I'm going to multiply that by itself once. If my money has grown 1,000 times, then I would have x is equal to 1,000, and you'll notice something about this graph. Even 1% interest will totally smash 100% simple interest, given enough time, which is what some of you guessed. How many of you are surprised that 1% interest after 1,000 years, let's just go ahead and find our intercepts, x is equal to 1,000 years, okay? Let's see how much more money that compound interest gave us. There's the intersection way up there. Way up. How much is that? That is times 10 to the 7. So 20 million. $20 million versus $1 million. Okay? It was not a little bit better, that 1% interest over there. It was better by a factor 20 after 1,000 years. Okay? Now, certainly, if you are investing according to human spans of time, like your lifetime, you would choose the simple interest every day. Look at that. Every day. Look, because you're probably going to want to use that money in like 40 years or something. And if you did, well, that $1,000 you invested would be worth $41,000 after 40 years. That's an amazing return on investment. 1% is going to be crushed by that. Now, 1%, that could be more interest than your savings account is giving you. It's still a significant amount of interest, especially when you look at what compounding does over time. Okay, so that's just a little break to take a look at how money works. These are both functions. For any value of x, they return one and only one value of y. So they are functions. Money, functions, function-wise. So we can use functions to help us understand money. Okay, rockets. Here is an example of how much acceleration a rocket is under. You notice after liftoff, the acceleration grows very quickly until it's reached a G level of about 5, and then that phase of the rocket will be detached. And then another rocket will fire up and slowly continue accelerating the rocket until it detaches, and a third rocket will then accelerate the rocket towards the moon or towards Captain Kirk or off into the great unknown. But in any case, there's so many examples from engineering, from science, and from physics that we can analyze with functions. Finally, music. I chose a very simple picture of sound. We'll recognize this later on as we start looking at trigonometric functions. This is a sine wave, and it's created by the sine function, the relationship between the opposite side and the hypotenuse of a triangle. And you'll notice it's a wavy form, and this is a wavy form. This is a lower pitch sound. This is a higher pitch sound. And these are also functions that we can use to analyze music. And there's only one example of how we might analyze music there. You could do number of hours practice per week and number of notes that you're able to play in a single bar. Maybe your speed increases quite a lot because you practice more. That would also be a function. Anyway, so based on the definition of a function, every x value must have a unique y value. That's the symptom of definitely that's a function. Okay, if I can look, it only has one y value for every single x value. In other words, if we're looking at a table of values or a list of ordered pairs, any single x value should only appear once. If we see an x value repeated, particularly when those x values create different values of y, we know that we're looking at a relation and not a function. Okay, so this is how we recognize a function from a table of values. So I'll go give you a chance to copy down that definition in your chart, and I'm going to do the same myself, and you'll see me working down here. So now, carrying on, let's take a look at these examples, and we'll see if we can verify function, not a function. So here I see, what are my possible x values here for this relation? Yeah, that's great. So I just read the first pair of the different numbers, and I have -2, -1, and 2. Because no x value repeats, this is a function. Over here, do I have any values of x repeating? No. So it's also a function. What's the problem with this one? Why are we saying that this is not a function? Yeah, there are 2 1s, and even worse, they're kicking out different values of y. Okay, so we can be sure that that is not a function. If I were to graph that, it would look a lot like this chart we created about number of hours studied and marks. The average, there can only be one average at any x, so that is a function. But my data included several values for each x, so that would be a relation, not a function. Okay, so that's how I do it with a table of values. Now, if we have something called a mapping diagram, mapping diagrams are useful ways to think about functions, particularly as you're visualizing a series of tables of values. And this has one of my favorite pictures. And this picture is going to help us understand what a function is doing, particularly tomorrow when we look at a new type of notation for functions called function notation. All right. Now, a function is a mathematical machine that takes your input and gives you a single output for any given input. Okay, and it shouldn't be a surprise as to what your output is. It should be determined. So an example like this that can help you understand is a vending machine. If I put in like my $1.25 and then I input H3, I should get the $1.25 item that's in slot H3. And H3, that should come out. My input of money is therefore transformed into a bag of chips. Okay? It would be a pretty weird vending machine if I put in $1.25, I pushed H3 and I got a random candy, or I got one of Smarties, chips, or Kit Kat. Okay? No vending machine works that well. Maybe some do. Maybe there's some like Las Vegas slot machine style vending machines that return multiple outputs for a single input, but I think personally that's pretty weird. Okay? So a function is something that takes your input and transforms it into a single output. Does that make sense? And here we have a function. This function of this line predicts, if you put your input in as I study about 8 hours a week, I can say, well, you're likely to get about 72% average. Okay? There's a single output for whatever input you put in. And so that's the function machine. Okay? Now a mapping diagram, it's if I go back there, it's a representation of the input values of a relation and the corresponding output values of the same relation. We say mapping diagrams represent a function when no x value corresponds to more than one y value. It's the same as a table of values. No x value corresponds to more than one y value. So you could copy that line down as well in that box, or maybe you already have it. Okay, so I'll just pause there and let you copy. So here are some examples of mapping diagrams. We'll notice here on this one, here we have all our x values organized in numerical order from largest to smallest. And even though two different x values are producing the same y value, that can still be a function, because no x value is producing two y values, two different ones. But over here, this one, why is that not a function? Well, if this one's a function, why is that one not? Suraj.
-1 is producing 3 and 4.
Yeah, -1 here can produce two different values. So then when we have a mapping diagram, we can see if there's any one x value that has this like double line coming out of it predicting two different things, that's not a function. So very good. Okay. So now let's take a look at some more stuff. Now, we can also apply what's called the vertical line test. You're going to want to write this down under graph. We use the vertical line test with our graphs to determine, are they a function? Okay? And now you can remember horizontal is left and right, vertical is up and down. So you may want to copy that as well. So I'll just pause while you copy. Okay, so while you're copying that, let's take a look at our example up here. We have a relation that's graphed on the board and a function that's graphed on the board. Here's my vertical line. Okay, I'm just going to use the ruler. We talked about a circle being a relation, not a function. You see how it doesn't pass the vertical line test. A vertical line can hit the relation at 2 points, therefore it's not a function. Recall that vertical lines on the xy plane are just like x equals 15. This is the line x equals 15. If that produces two y values, sorry, no go, it's not a function. Now, if I look at my scatter plot with the different data points, clearly, those data points line up vertically. So it's not a function. It can be a relation, but it's not a function. The line, on the other hand, and in fact, any line that's not a vertical line will be a function. Okay, so this line, doesn't matter where I put this vertical line, everywhere along its domain and range, I only produce one y value for any x value. This vertical line only touches it at 1 point. Therefore, it's a function. And that's the visual test that you can do on a function. Just imagine a vertical line going across. Now, there was some debate over whether a parabola would be a function. So I'm just going to deface what we did here because I don't think I need to refer to it much more. I'm just going to draw a big parabola there. Okay, now, even though if I were to look at horizontal lines, a single y value can be determined by more than one x value, but that wasn't what we talked about. It's a vertical line test because we're looking for the independent variable, no matter where it is, to only produce one y value. So each independent variable, any value of x, will only produce one unique y value. Passes the vertical line test. Okay? So therefore, a parabola is also a function. And we looked at sine waves, music, also a function. Exponential curves, also a function. We looked at examples of those as well. Okay, let's carry on. So now here, when we take a look at these two, we'll see this one is a function because when I take that vertical line across, this one passes. There's only one y value for any given x value. This one, a circle, definitely not a function. Okay, let's carry on. Now, if we're looking at an equation, equations, we can also look at them and see, is this a function or not? So when we were looking at lines, we had y equals mx plus b. That has one x value for every y value, and we look at an example up here. And then a quadratic given by y equals ax squared plus bx plus c. There might be as many as two x values for every y value. There is one place where there's only one. One x value gives you one y value, and that's the vertex. But otherwise, every x value gives you two y values because of this squared. So what do you notice about the power that x is being raised to and the number of x values that could be? Here, this is x to the 1, and every y value has exactly one x value. Here, this is x squared, and every y value could be two different x values. So do you see the relationship there? That when I have something squared, I could have as many as two solutions for x for a given y. That pattern's going to continue as I raise the power of x. So if I have ax cubed plus bx squared plus cx plus d, okay, so now I've added an ax cubed to the front of this, I could have as many as three solutions. 4 solutions if it's x to the 4, 5 solutions if it's x to the 5. Those are functions that wiggle a little bit, so a single y value might have multiple intersection points. But when given an equation, if the exponent on the y variable is the power of 1, okay? Here we have y to the 1, y to the 1, okay? When you see y to the 1 equals, then you know, and there's no plus or minus in there as well. If there's a plus or minus, that can complicate it, because that can return different answers for the same x. But when y equals something, and that's to the power 1, there's only one y value for each x value. Okay? Therefore, when you see y to the 1, that's a function. Notice that your equation for a circle has a y squared in it. Even if I take the square root of both sides, I will have a plus and minus on the other side. So the single x value can output two y values, not a function. Okay, carrying on. So here, if we look at these, this one, why is that not a function? Because we have y squared. And that's all we need to be able to do to see if I have an equation, if y is to the power 1, then we have a function. Anything else, if it's y to the 2, it's not a function. This one is a function, y. Why is that a function? Y is to the power 1. This is also a function. And we haven't talked about this one yet. Y is equal to 1 over x plus 3. That's a function. Because y is to the power 1. And that's all we need to be able to recognize when we're looking at an equations. Okay? So just to recap what I have here on my handout now, is I just have something that looks like this. Okay? And that's going to be enough for me to remember what we've taken a look at. Where? Oh, it says y is equal to the power of 1. If y is being raised to the power of 1, that's a function. If y is to the power 2 or more, or we see a plus minus. If we see a plus minus in the formula, that can be a symptom of actually having a y that's squared. Okay? Then this is a relation. Relation. There we go. This is a relation, not a function if we have y to the power 2 or more. So I'll give you an example of where we might see a plus or minus. We saw y squared plus x squared equals 9. This is a circle with radius 3. So it looks like this on the xy plane. That's 3. Okay. Notice it does not pass the vertical line test. I can touch it at 2 points there. Now, if I were to rearrange this, I could subtract x squared from both sides. Sorry, I'm there. Shouldn't autofocus on you anymore. Sorry for seasick. So I'm going to rearrange this to have x squared on the other side. So out of y squared equals 9 minus x squared. And then I'm allowed to take the square root of both sides. So that would, if I take the square root here and the square root here, I would have y is equal to plus or minus the square root of 9 minus x squared. Okay? That would not be a function because of this plus minus. Okay. Do people want to see that graphed? Sure. Okay, let's graph it quick. So if I go over here to Desmos, circle. So notice I've graphed y equals the square root of 9 minus x squared. Notice that I have half of the circle. Is that a function? Does it pass the vertical line test?
Yes.
I'm seeing some nodding heads. Yes, it is a function. Half of a circle is a function. Okay? Now, let's copy this. Copy, and then graph it again, but with a minus. Now, notice what I've effectively done is put in that plus minus there, okay? I have graphed the top half and the bottom half. The bottom half alone is also a function. It also passes the vertical line test. Both of them together, that plus minus defeats the function test. That kicks out 2 y values. Okay? So that's why those things are happening. All right. So let's now carry on and finish up. What is a function? Present. Okay, so now let's carry on. I think we're just about done. So now here we are, practice questions. So these are the practice questions that you can complete. They are in your textbook, and your job is to state which is a function and justify your choice. Don't worry about domain and range or graphing yet. And that took a little too long. I am working on being faster. Thank you very much for showing up for your learning, and I hope that helps clarify why I'm so excited about functions.